In order to perform the SN2 portion of the experiment, you need to prepare a solution of nucleophile, which is going to be iodide in acetone. Now, we have no way of buying iodide itself, so instead we just simply use sodium iodide, which you can grab off the shelf and purchase, and we need to make a 600 milligram in 5.5 mils of acetone solution of this. As always, this does not need to be precise, so 630 milligrams of sodium iodide are going to go into my little test tube, and to that I will add 5.6 mils of acetone. I seem to have overshot a little bit, but we're talking about 5.8 mils of acetone. On the other hand, since I overshot a little bit with the sodium iodide, that's probably on balance a good thing. Now, one of the harder parts of the lab is to get that stuff to dissolve. So you can either stand here and sort of flick it, or you can get a pipette and suck it up and squirt it down, and so on and so forth. Simultaneous with this, I need to prepare a solution of 0.1 grams, so 100 milligrams of silver nitrate dissolved in 12.5 milliliters of ethanol. Since these test tubes won't accommodate that, what I'm going to do is put 50 milligrams in there with 6 and a little milliliters of ethanol. And again, I seem to have overshot. 65 milligrams. So maybe I'll use 7 milliliters of ethanol, give or take. Actually, this appears to be more like 65 milligrams or so. So now I need some ethanol. Just about 7 milliliters exactly of ethanol. And again, the best way to get these to dissolve is almost certainly to get my hands on a pipette and a bulb and to suck it up and squirt it down. Again, if you're trying to mix things such that they dissolve, this is by far the best way to do it if you're doing it in a test tube. Just suck it up and squirt it down. Nothing else comes close in terms of how fast this is. Okay, eventually I was able to get the nucleophilic solutions to dissolve. So over here in the back left, what we have is the silver nitrate in ethanol, which was remarkably difficult to dissolve, but it is finally in enough to use. And on the right-hand side, what we have is the sodium iodide dissolved in acetone. In other words, the SN2 style nucleophile. So now that we have those test tubes made, we are ready to go ahead and try some actual solutions. So from left to right, what I have is a test tube for the 1-chlorobutane, which is the primary chloride. Then next we have the 2-chlorobutane, which is going to be the secondary chloride. Then we have the 2-chloro-2-methylpropane, which is going to be the tertiary chloride. And then we have the 1-bromobutane, primary bromide, and 2-bromobutane, secondary bromide. So that's what's going to be going into those test tubes next. My initial attempt at this experiment using a bit more than the requested nucleophilic solution was not as effective as I would have liked, so I'm going to retry this. This time I'm only going to use the requested 10 drops for each of these, and even though that is a tiny amount of solution present, hopefully that will lead to the ratios being correct to observe what we want to observe. As the problem with this relatively qualitative experiment is we're talking about tiny amounts here, and it's entirely possible that the details matter more than I'd like. So those are the solutions in question, the nucleophilic solution present in each one. Now to that, I'm requested to add 8 drops of the electrophile, so the 2-bromobutane, and what you see immediately is a fairly cloudy solution that, as I'm holding this and shaking it, has immediately dissolved. So I'm not quite sure what to make of that. It was instantaneously cloudy with possibly some precipitate, but now it appears to have dissolved and is apparently a clear and mostly colorless solution. We will want to heat this one up, that is for sure. We're now going to add primary bromide to the next test tube. And again, what I see is an instantaneous cloudiness present. I also see a very distinct color change, but that is both cloudy and bright yellow. So that has unambiguously reacted in a fashion, although it does not appear to have formed necessarily much of a white precipitate yet, but something has clearly happened. We can definitely say that a reaction has taken place. All right, to the tertiary chloride test tube, I now need to add 8 drops of the electrophile. And somewhat oddly, I appear to have a bit of a cloudy solution. I do not actually appear to have any solid in that solution, but it does appear to be cloudy. Not much of a color change. We'll keep an eye on that. Adding electrophile to the secondary chloride now. And it was briefly hazy, but I would describe that as clear and essentially colorless at this point. 8 drops of the primary chloride coming next. And likewise, I would describe that as clear and colorless for the moment. Without heating, it is unambiguously the case that the 1-bromobutane reacted, and it clearly has done a substantial color change, and it is quite cloudy, and I can see visible solid up here, although that probably does not translate on camera very well. There is solid collecting in the bottom of the test tube, and that probably is visible on camera. There's a little bit of a white pellet down in the bottom there. So there is no need to heat up the 1-bromobutane. It has unambiguously reacted both in color and in the formation of a solid. All right, this is the tertiary chloride, the 2-chloro-2-methylpropane. So the tertiary chloride, terpbutyl chloride, does appear to have a hint of a solid formed, and this is confusing because it shouldn't. So let us now add 4 drops of the nucleophile according to the troubleshooting procedure. And after I added the few drops of the nucleophilic solution, the acetone, what I've noticed is that the solid appears largely to have dissolved. And so we are back at a yellow but hazy solution, but with no visible solid floating in there. But it is clearly time to heat up all of the solutions that contain no visible solid and see if anything happens. Secondary bromide, 2-bromobutane, is headed toward a reaction. It is cloudier than the chlorides. Not as cloudy as the tertiary chloride though, so that's odd. Here we have a water bath at 53 degrees, and the reason why that's important is because it is very similar to the boiling point of acetone. So in other words, what we're doing is heating up these solutions very close to the reflux temperature for acetone, and we're supposed to let them sit in there for several minutes in order to see if anything happens. After heating the system, I believe it's safe to say that the secondary bromide has reacted. This clearly contains, by eye anyway, a pellet of white solid in the bottom. It's relatively difficult to get that rotated in such a way to have it show up on camera, but it's there, right at the bottom of this test tube. As I rotate it, there's a small white pellet of solid. So the secondary bromide clearly reacted, although it reacted substantially slower than the primary bromide, which I'll recall happened almost instantaneously. The primary chloride likewise has formed a bit of a film of white around the edges here, and it's very difficult to see on camera, but the glass itself is marked with this white, and there's a tiny amount of white precipitate that's probably best visualized if I point the test tube at the camera like so. So there are tiny little dots in there as well as the band of white that you can see. The secondary chloride behaved rather similarly to the primary chloride. There's little white dots and there's a band of white around there. And then the one that doesn't make any sense at all is the tertiary chloride, which should not have reacted, but this went yellow almost immediately and cloudy and hazy, which to me suggests nothing so much as a bit of an impurity present. Can't be sure about that, but that would be my instinct. All right, so the upshot is that the primary bromide reacted first almost instantaneously, very, very fast. The secondary bromide had a likewise relatively quick reaction once I started heating it, but required heating in a way that the primary bromide did not. The secondary bromide was faster than either of the 2 chlorides. The 2 chlorides, the primary and the secondary chlorides, are more similar to each other than not, both in appearance now and in how long they took to react. And then the tertiary chloride turned yellow immediately and cloudy, and now is sitting here, which is to say no visible solid, but definitely yellow. I imagine the yellow is due to some impurity reacting with the nucleophilic solution, perhaps a primary chloride that's present. Just to summarize the observed results in the table that would be present in your handout if you were there, I would say that the 1-chlorobutane did not react at room temperature, neither did the 2-chlorobutane, whereas the 2-chloro-2-methylpropane went yellow and hazy almost instantaneously, and it's not clear to me whether that constitutes a reaction or not. Again, my interpretation is that it's some impurity, but there clearly was a visible change, so I should record that as part of the data. Now, it is my sense that the instant color change and precipitate that formed in the 1-bromobutane is a real finding, and therefore I believe it. And then I would note that the 2-bromobutane did not react immediately, but by the time we went over to the rotovap to try to heat things up a bit, this had already started to form a precipitate. It was definitely hazy at that point, no color change, but a precipitate had started to form. I didn't make a big deal out of it over the camera because it wasn't particularly visible, but it was my sense that I was seeing precipitate at that point. Meanwhile, upon heating, the tertiary chloride didn't really change all that much. We didn't bother to heat the 1-bromo, and the white solid definitely got much more intense as soon as I heated it up at all. So that's this notation here. It wasn't possible to draw distinctions between the 1-chloro and 2-chlorobutanes. They did clearly both form precipitate, very similar amounts, and it was my sense that that was happening nearly simultaneously. So there wasn't much of a distinction between those two. I did want to mention for the record that though I consider this experiment to be a decent one for trying to convey some certain principles, I don't think it's the right way to figure out if these reactions are working as well as you'd like. And what I mean by that is that this tertiary chloride appears to have reacted because you had some yellowish and a bit of a haze show up. And the reason why it's confusing is because a small amount of an impurity would be enough to cause this. And in fact, I think that's what's happening. If I wanted to know for sure if these reactions were taking place, what I would do is take 500 milligrams or maybe a gram of each of these substrates and add to it sodium iodide and acetone and run the actual reaction and purify it explicitly by using column chromatography and get my hands on the actual stuff. And then I would know based on a yield how well these reactions ran. And when I did that, I would be very surprised if I got a meaningful amount of the tertiary chloride. I would probably get zero. I probably wouldn't be able to isolate any of it. But if I did isolate some, it would only be tiny amounts, whereas these other reactants would work great and you'd isolate meaningful amounts of the compound. That would be the way I would do this if I really wanted to know. The problem with that thought is that each one of those experiments I just described, actually running the Finkelstein reaction with sodium iodide and acetone on each of these substrates, takes about a lab period for each of you to attempt this. And then we would have to spend at least a lab period doing the purification with the column chromatography and everything else. So in other words, we would have to devote 2 lab periods for each of these substrates. We could spend the entire semester if I wanted you to experience all of this for yourself. And even if we divided and conquered and used this across the class, it's still devoting at least 2 weeks to the proposition, trying to figure out if these work or not. By contrast, of course, if we do this on small scale, we get an immediate readout. The problem is that it's qualitative. And because of that, we can't be sure when we see something, is it due to the reaction that we're trying to study, or is it something else? I do want to show you something. This is the kind of chemistry that I have run in my previous career to make a similar sort of reaction happen. I had a need for this alkyl iodide, this actually allyl iodide, because there is a double bond there. So I needed to make this stuff. But the reason why I'm showing you this is now that you're moving on to SN1, SN2 reactions, I wanted to show you that this kind of synthetic operation is something that we use absolutely all the time in graduate school. And in fact, a lot of the chemistry that I've illustrated here is stuff that you're going to learn about in the next couple of weeks if you haven't learned it already. So I needed to start with this particular triple bond diol because it was really cheap and the easiest way to access the material I actually wanted. But the problem was that this is a diol and I only wanted to convert one of the alcohols into the iodide. So I first needed to cover this up with something else. And as it turns out, TBS chloride, which is a way of installing a silyl group, protecting group that hides one of the alcohols, is the way that was the most cost-effective and easiest to do what I wanted. But then comes a reaction where you convert a triple bond into a trans double bond. When you learn about this reaction, you will probably learn that sodium and ammonia are the best way to accomplish this transformation. And again, I would expect you to learn that in a couple of weeks. But in practice in the lab, another way you can do it is lithium aluminum hydride, and that is more straightforward reaction, so that's what I did. Moving this material just straight down here, what I then needed to do was convert this alcohol into a better leaving group. And in the next couple of days, you're probably going to learn about how you can convert an alcohol explicitly into a leaving group that's not a chloride. One of the ways you can do that is by adding methane sulfonyl chloride and triethylamine to make this mesylate, methane sulfonate. This is now an excellent leaving group, and though it's not a chloride, so it doesn't exactly match what we did in the lab, it's close enough so that I could convert it by using sodium iodide and acetone into the desired iodide material. Now, I've actually run this reaction on very large scale with like liter-sized flasks of the material and huge columns, and it was a giant pain in the butt because this material turns out to be light sensitive. And in fact, every single time I ran this reaction, I would make some batch of orange material first, kind of like that bromobutane. But over the course of chromatography over maybe 2 days in the dark, I would eventually end up with a smaller, much smaller amount of stuff that was either colorless or very faintly yellow. So my colorless or faintly yellow material I could then carry on and do actual other chemistry with. On large scale, I promise that this sort of chemistry works, and I promise that a primary substrate, especially a primary and allylic substrate like this one, will react quite effectively under standard SN2-like condition. Again, I used it to make hundreds of grams of this material because I needed to use this stuff for subsequent reactions.